In this video, I want to prove that the Fisher information matrix can be computed as the Hessian matrix of the log likelihood function or via the squared Jacobian, both evaluated at the MLE estimate. So here in more detail. I'm going to show that for a maximization problem, you compute the Fisher information matrix either by using the expectation of the Jacobian of the log likelihood function to the power of 2, or as minus the expectation of the Hessian of the log likelihood function. Now let's show that at last equality sign holds. So we define f to be the likelihood that depends on the data x and the parameter theta, and to shorten the notation, we just say f is a function of theta, because that's the parameter vector. Yeah? So we ignore the x. Now we are now going to rewrite minus the expectation of the second derivative of ln L, where the derivative is taken with regard to theta, as minus the expectation. Now we take the first derivative of the product, and the product already is now the first derivative of the log likelihood. So it's 1 over L times the inner derivative, which is the change in the likelihood over theta. Now what we now do is we are now swapping L with f, just to simplify notation. And now we use the product rule to make a second derivative. And if you do that, you end up with the expectation of 1 over f to the power of 2, f prime, where the prime is the first derivative, minus 1 over f double prime. So it's a second derivative. Now, if you look at that now carefully, you see that the first term can be rewritten as the expectation of f prime over f to the power of 2. And the last term just remains as it is. It's minus the expectation of f double prime over f. Now looking at the first term again carefully, you see that is just the derivative of the log of f. So therefore we can write that as the expectation of ln f prime to the power of 2. And the second term remains as it is, so it's minus the expectation of f double prime over f. Now I'm going to show you in a minute that the second term is 0. Meaning we end up with the expectation of log f prime to the power of 2, which is the information matrix. Now let's show that that equality sign truly holds. So what we do is we now explicitly look at the term minus the expectation of f double prime over f. Now what do we have? We have the expectation, which we are now going to write as an integral from minus infinity to infinity times the density. And f double prime we're going to write as the second derivative of f. Now the integral and the differential operator can be swapped. These are both linear operators. So therefore we rewrite that term as minus the second derivative with regard to theta of the following term. The integral of minus infinity to infinity of f times the density f divided by f, and now we integrate with dx. So you see there's some cancelling going on, so the f in the numerator and the denominator cancel off. You end up with the integral of f dx, which is just 1, and the second derivative of 1 is just 0. So indeed the second term has been 0. And that kind of shows that from an analytical point of view, you really determine the information matrix either by the squared Jacobian or by the Hessian, whatever turns out to be numerically more stable.